So this lesson is about what I like to call the train tracks theorem. You're going to see why these look like train tracks receding into the distance. The official name that you'll sometimes see in a textbook is called the proportional segments theorem. That's not very catchy. Let me show you how we get at it. Here I have three parallel lines inside this large triangle. And because these parallel lines make congruent corresponding angles, these three triangles, the littlest one, the middle one, and the biggest one, are all similar. So if I draw them separately, so I can do some calculating, the littlest one is 1 and 3. The medium one is 1 plus 2, 3, and 3 plus x. And the largest one is 1 plus 2 plus 3, 6, and then 3 plus x plus y. And I can use similarity to figure out what x is, and then once I know what x is, I can figure out what y is. I can see here the ratio of these triangles is 1 to 3, from this one to this one. So 1 to 3 ratio. So that will let me to get x. 1 to 3 is 3 to 3 plus x. Cross multiplying, I get 1 times that, so it's 3 plus x equals 9. So x must be 6. So if I'm back up here, this is 6. Now that we know what x is, we know this is 3 plus 6 plus y, or this is 9 plus y. And now we can use these two similar triangles to figure out what y is. You can say 1 to 6 now is 3 to 9 plus y. Again, cross multiplying gives me 9 plus y equals 18. So that means y is 9. Coming back up here, this is 9. So, and I want us to observe something here. What I want to observe is that if I look from the left-hand side to the right-hand side at each of these pieces, going left to right, there's a constant ratio. There's 1 to 3. This is 2 to 6, which is also 1 to 3. This is 3 to 9, which is also 1 to 3. This is even true if I add, like 2 plus 3 here is 5. 6 plus 9 is 15. So 5 to 15 also reduces to a 1 to 3 ratio. So when I run these parallels across here, apparently this side-to-side ratio between corresponding segments is the same. That's why this is called the proportional segments theorem officially. When you put parallel lines across here like this, these segments that are created are proportional to one another as you go from one side to the next. And for this to work, you don't even need the triangles. These segments here don't have to meet. When parallel lines cross through a pair of segments, these are parallels here. This is why I like to call it the train tracks theorem, because it looks like train tracks sort of receding off into the distance. When parallel lines cross through a pair of segments, the segments are divided proportionally. What this means is if I look at, say, each of these segments in turn, it corresponds with a segment on the other side. Now these segments aren't equal. That's why I'm using different symbols here. These segments aren't equal. This segment here is longer than this, but the left to right ratio between any pair of corresponding segments is always the same. So the left to right ratio between corresponding segments is constant. It's always the same. And so it's constant. There we go. So we can use these proportionalities to find missing segment lengths. Let me show you an example, and hopefully it will make things clear how we do this in practice. So I put the figure on its side just so we get used to things being different. So in this picture, all of these lines are parallel. AW, BX, cy, dz. All these are parallel, so we're going to be able to use the train tracks theorem here. I give you some measurements. Let's put those in the diagram. AB is 4, so A to B is 4, that distance right there. B to C is 6. W to Y is 15. Okay, that's kind of obnoxious. So that's like from here to there is 15. And YZ is 12. And we're going to determine CD and WX and XY, all those unknown lengths. So the train tracks theorem tells me that here it's top to bottom. The parallels are going up and down. So train tracks theorem tells me the top to bottom ratio between corresponding segments is always going to be the same. So I need to find a pair top and bottom where I know both lengths. Because that will establish the ratio. And I only have 2 lengths down here at the bottom. I have 12, but I don't know the value here for CD. And I have 15. But I do know what this is up here that corresponds with the 15. 15 goes from W to Y, and if I follow the parallels up, it lands on A to C, and A to C is 10. So there's my corresponding pair. I have 10 on the top corresponding with 15 on the bottom. So that tells me the top to bottom ratio is 10 to 15. And this reduces by dividing top and bottom by 5 here. This is 2/3. So there's a 2 to 3 ratio top to bottom. And then I can just quickly set up proportions to solve for each of my unknowns. To get CD, CD's on the top. So CD over 12 is in a 2 to 3 ratio. Cross multiplying this, I get 3 CD is 24, or CD is 8. That's CD. How about WX? WX is on the bottom. It corresponds with AB on the top. If I follow the parallels up, WX maps onto AB. So that means AB, which is 4, over WX is 2 to 3. And by inspection, I can see WX must be 6 here. 4/6 is the same as 2/3. And then finally, XY. XY is on the bottom. Following the parallels up, I see it maps with 6. So 6 over XY, that's top to bottom, again is 2 to 3. Cross multiplying, I get 2 times XY is 18. So XY is 9. And this is how the train tracks theorem works. You look for a pair top and bottom here where you know both lengths. That establishes the ratio top to bottom, and then you keep setting up proportions to find each unknown using that ratio over and over and over again. One last comment on this, and that is the train tracks theorem tells us nothing about these lengths joining here to here. This 2 to 3 ratio top to bottom has nothing to do with how long these are. And the easiest way to see that is we could imagine taking this segment here and sliding it down, keeping it parallel, making all of these segments here longer, the up and down parallels longer, without changing WX or XY or YZ, so that this 2 to 3 ratio is maintained top to bottom without telling us anything about these lengths, because I can alter these lengths as I see fit, making these lengths of the parallels change without altering the 2 to 3 ratio. So the train tracks theorem doesn't tell us anything about these lengths of the connecting parallels. In order to do that, I would need to connect these and get some of these lengths and make similar triangles to start working out what these lengths are. But that's from a previous lesson.